In this lesson, I'll show you two examples on how to determine a parametric representation of a single line that's in rectangular form. Notice in question number 1, we have y is equal to negative 2 over 3x plus 5. And what we want are two parametric equations that represent just this. The steps doing this are shown underneath. We'll start with step number 1, which says determine the slope of the line and identify x initial, y initial, where we have this point is the initial point. Now in question number 1, unlike in question number 2, they don't tell us the initial point for this equation, so we will be skipping this part in particular of step 1 and only identifying the slope. But in step 2, we'll be going through all of this because the question is more thorough. So step number 1, the slope is this part of the equation. This is in slope y-intercept form. We have mx plus b. That's the y-coordinate of the y-intercept. Okay, so we have negative 2 over 3 is equal to m, which is our slope. And slope is a measure of change of y over change of x. So I have change of y is equal to negative 2 and change of x is equal to 3. Now, since they don't tell us the initial point, what we could do is use the y-intercept. We can say that the y-intercept is the initial point. I'll write down that the initial point is 0 and 5 because the y-intercept is at positive 5 and the x-coordinate would be 0. So that's x initial, y initial. In step 2, determine delta y and delta x. We just did. That's done. Step 3, determine the parametric equations in these two forms. That's important. So our very first parametric equation will be x is equal to x initial, which we said to be 0, plus delta x, 3 times t. This simplifies to 3t. For the other parametric equation, I have y is equal to, this time y initial, which we set to be 5, plus delta y, that's negative 2 times t, and this simplifies to negative 2t plus 5. These two are the two parametric equations that represent the original rectangular equation. I'm skipping step number 4 because the question did not give us any restrictions, and this pertains to when we are given the restrictions and the terminal point, which you see in question 2. Determine a parametric representation for the linear equation, this one, and the restriction is between negative 1 and 3 over 2, such that the initial point is 3 over 2, and the terminal point is negative 1 and 5. As you see in this question, they give us the initial point. It's at 3 over 2 and 0. So 1.5 and 0, that will represent x sub 0 and y sub 0, which we didn't have in question number 1. Another problem that we face here is that this question, 2x plus y is equal to 3, is not in slope y-intercept form. So let's make it in slope y-intercept form by isolating for y. We have y is equal to 3 minus 2x. And now we can easily identify our slope, which is negative 2. M is equal to negative 2. I'll write this down as a fraction, negative 2 over 1. But unlike in question number 1, we can't automatically assume that this negative belongs to the top number as opposed to the bottom number. Instead, what you have to do, and I know this part is a little strange, is you have to look at the initial point and the terminal point to be able to determine which one is negative, whether it's the top or the bottom. So if the initial point is 1.5 and 0, let's take a look at this on an xy plane. If the initial point is at 1.5 and 0, which is approximately here, and the terminal point is at negative 1 and 5 up here, this means that the data is going from right to left. So the y's are increasing, they're getting more positive, whereas the x's are becoming more negative. They're going from right to left. This means that this negative belongs to the negative 1. So delta x is negative 1 and delta y is positive 2. You have to do this check when you're doing your question. Okay, given what we now learned, we can create those equations like we did in question 1. We have x is equal to, our initial point was 1.5. So 1.5 plus negative 1t, and this simplifies to x is equal to 1.5 negative t or 3 over 2 minus t. And the other equation is y is equal to, we had 0 plus 2t. So y is equal to 2t. These two equations are the parametric equations that represent the original rectangular equation. Okay, step number 4 says restrict the parameter using the form 0 is less than or equal to t less than or equal to big T. And we have to find out what big T is. To find out what big T is, I'll take the terminal end, which is at -1 and 5, and I'll use any one of these equations. Let me use this one for simplicity's sake. And I'll place the 5 right here. 5 is equal to 2t. And I'll replace this little t with big T. Because remember, t is the value of the parameter corresponding to the terminal point. So solving for big T, we have 5 over 2 is equal to big T. I can replace that now with 2.5 or positive 2.5. These two are the parametric equations that represent the original equation, and this is the restriction. And interestingly, had you not used this equation and used this one instead, having put -1 into here, remember the x coordinate of the terminal point, and solving for t, you would have ended up with, again, 2.5. So there you have it. That is how to determine a parametric representation of a plane curve that is defined by a rectangular equation.